This is the second video in Unit 7. Okay, so we're going to still talking about gravitation, but now we're going to look much more at gravity from a potential energy standpoint. Okay, we have several learning objectives and essential knowledges, and as well as numerous formulas. These formulas are not actually going to be provided on the formula sheet, and it's actually much more important for you to know how to derive these formulas because they will play around with with different variables, and you need to know what each variable stands for and derive the new equation. Okay, so here we have the formula for potential energy on the right-hand side, as well as the learning objective. You can read these learning objectives and the essential knowledge associated with them at your own leisure. Okay, here's the third page, and here's the fourth page. So here's the formula sheet again. Okay, on the left-hand side are IB versions as well as a integral form of potential energy, but really only the two formulas on the right-hand side are part of the formula sheet. Okay, so 7.2 is primarily talking about Kepler's laws and potential energy. Kepler has three laws, the first of which is that the orbits of the moon and the planets are elliptical. Most of the time we'll be looking at just circular orbits, but a circle is also an ellipse. Okay, it happens to be a trivial ellipse in the same sense that a square and a rectangle are related. Okay, so a circle is related to an ellipse the same way a square is to a rectangle. Both sides happen to be equal. The second one is actually going to be about conservation of angular momentum. So what we learned in Unit 5 about angular momentum carries over to this unit. Okay, and basically if we think of it as r cross p, then that stays constant the whole time that the orbiting object goes around its orbit. Okay, it's also easy to think about it that as the object gets closer to the orbited object, the speed increases. The last one is the law of periods, where t squared over r cubed, where t is period and r is the radius of orbit, is going to equal 4 pi squared over gm. Okay, and we'll see the derivation for that, and it's important to learn that derivation. It's relatively simple and makes a lot of sense, but you do need to know how to do that. So, first law basically says that all gravitational orbits form an ellipse. Okay, the orbited object, however, sits at one of the two focal points of the ellipse, not at the center of the ellipse. Okay, the orbited object is actually going to be the center of mass of the system, and there's a PhET simulation that goes along with it. Okay, but it's important to remember that both objects, okay, both the orbited object and the orbiting object, both of them actually orbit the center of mass. For most of the situations that we'll encounter, though, the orbited object is so much more massive that its center of mass is effectively in the object itself. If you're confused over focal points, what that is, here's a picture of an orbit of a planet and its elliptical orbit around a sun. Okay, notice the sun is at focal point 2. It is not at the center of the circle, it's at focal point 2. A couple other definitions here are perihelion and aphelion, and the major and minor axis. But primarily, just understand that we do not put the sun at the center of the ellipse, but rather at one of the focal points. For a circle, the center is the focal point, and both focal points are at the same place, the center. So this is Kepler's second law. Okay, Kepler's second law is basically a statement of conservation of angular momentum. It basically says that the angular momentum, r cross p, of the orbiting object is a constant. Sometimes you'll see it expressed in a very complicated form. I'm not quite sure why we go with this form, but it does show up in many textbooks. In this form, it basically says that the area swept out by the orbiting object in the same amount of time is a constant. So in this case, area 2, which is close to the sun, so the object is going faster, versus area 1, where it's going slower. Both of those areas are going to be the same. Now, in general, we don't really know, we don't necessarily learn how to calculate sector areas for an ellipse. So really, let's just stick with R cross P. Okay, at perihelion and aphelion, R and P are going to be perpendicular. So at that point, we don't really need to worry about the sine theta aspect of R cross P, and it just becomes R times M times V for the planet. Kepler's third law is basically that t squared over r cubed is some constant. That constant happens to be 4 pi squared divided by capital G, our gravitational constant of 6.67 times 10 to the minus 11, and m, where m is the mass of the orbited body, okay, the sun in the previous diagrams. Okay, and this formula can be derived from Newton's law of universal gravitation combined with centripetal acceleration. There is an assumption that the orbit is circular. For most of the planets in our solar system, they're pretty close to circular. Okay, so this is the derivation of Kepler 3. Okay, like I said, it starts with gmm over r squared, which is Newton's law of gravity, universal law of gravitation. And since gravity is the force making the planet travel in a circle, F sub g is also going to equal little m v squared over r, where little m is the orbiting object, okay? It's the moon in the case of the Earth-Moon system. Capital M would be the moon, Earth, mass of the Earth. So we set those two equal, and we can replace the velocity of the moon, okay, the velocity of the orbiting object, with circumference divided by period. Since it's moving in uniform circular motion, v stays constant, and the distance divided by time, or circumference divided by period, gives us its velocity. And so here we have 2 pi r over t, circumference divided by period, okay, and we cancel little m because little m's on both sides. Okay, continuing this, expanding my 2 pi r over t and simplifying the fraction, the left side becomes 4 pi squared r over t squared, and that's going to equal gm over r squared. Cross multiplying gives us 4 pi squared r cubed is equal to gmt squared, and then putting it in the necessary format, we have t squared over r cubed is equal to 4 pi squared over gm. Okay, so that's the derivation of Kepler 3, and we're going to see this aspect of setting gmm over r squared, Newton's gravitational law, equal to centripetal force throughout this unit. So it's important to know that derivation and what the various letters stand for. Okay, in particular, it's going to be important to realize that little r in mv squared over r is the radius of the circle. It's the radius of the moon's orbit. Capital R, however, is the distance between the objects. Little r and big R are not always going to be the same. We'll see that when we start doing binary star calculations. The other aspect of Unit 7.2 is going to be potential energy. Okay, close to the surface of the Earth, we've calculated potential energy primarily as mg delta H. Okay, but far from the Earth, the force is not constant, so we would need to do some calculus, integral calculus actually, to find the area under the curve, to find the work as the object moves from point A to point B. Okay, so remember that the area and work is going to be calculated using force times distance times cosine of theta, but you're going to need to pay attention to the direction of force and displacement. As the object moves closer to the planet, okay, gravitational force is always going to be attractive or towards the planet, and the displacement is that way. Work then would be positive. My object is going to accelerate. Okay, however, if the object is moving away from the planet, gravity is still towards it, but the displacement is away, my work is going to be negative. My object is going to lose kinetic energy as I move away from the planet. Okay, so remember to double check the directions of your two vectors in this formula, okay? Force and displacement to determine whether work is going to be positive or negative. Okay, so formula for potential energy is basically going to be minus G capital M lower m over R. Okay, if I use the formula for G, it becomes minus GmGr, which is very similar to what we saw for MgH. Part of what confuses people here is the fact that your gravitational potential energy is always negative in this formula. Okay. And part of the reason is that by convention, everybody agrees that at a distance of infinity, okay, my potential energy is going to be zero. Meaning, if I think of altitude as gravitational potential energy, kind of an MGH type of view, that's as far as I can get, infinity. Okay, and that's when I'm going to have the most potential energy. So if I set that point to be zero, every other point then must be less or negative. Okay, so what that also means is that I need to add energy to separate the two objects, to get the object, the little object, all the way away from the planet so that it can get to infinity. Okay, so this is what a graph of the potential energy looks like. Notice that it is entirely negative, and it goes and is tangential, asymptotic to zero. Okay, and just like forces, potential energy can add. It is a scalar, so I don't need to worry about direction. But when I have two objects like this Earth and the Moon, I add the two and I end up with the blue graph in this picture. Okay, and this graph is similar to a potential energy graph or a hill type of graph when we did energy way back earlier in the year. So this is similar to the situation where I have a block of mass m and speed v approaching a hill of height h. And the question is, does the block make it over the hill? What this means for astronauts and NASA is that I only need enough energy to get past the hump on the blue curve. Once I get past the hump on the blue curve, then the moon's gravitational field takes over and I end up not needing as much kinetic energy as you might suspect. Okay, and so energy of an orbit. Okay, the total energy of an object in orbit is going to be the sum of both its kinetic energy and its gravitational potential energy. Since gravitational potential energy is negative and kinetic energy is positive, the total energy must be less than or equal to zero. Otherwise, it implies that your kinetic energy is greater than your potential energy, which also means that the object has enough kinetic energy to escape the gravitational field. And this is going to be what we call escape velocity. And if it has that, it's not going to be orbiting. It can basically go wherever it wants. So we end up with 4 rules of circular orbits. Really, there's only one rule, but the other 3 can be derived from the fact that total energy is the sum of kinetic plus potential. This is the rule that I would prefer that you memorize. Okay, it's basically, and we'll show the derivation for this. Okay, but negative kinetic energy is going to equal half the potential energy. Remember, kinetic energy is positive and potential energy is negative, so I need the minus sign. Okay, and during a circular orbit, your 1/2 mv squared is basically going to equal 1/2 gmm over r. Okay, and we'll show the derivation. The other 3 forms here are simply substitutions for total energy and looking at it in a different way. I think the best way to remember it, though, is that first one. Okay, you can look at these at your leisure. Okay, so the derivation of the rule, where does that come from? Again, I'm going to set the centripetal force mv squared over r equal to gmm over r squared. So here's the mv squared over r, centripetal, going to equal gmm over r squared. Let's simplify that. Okay, and so v squared equals gm over r when I cancel various variables in there. Okay. Remember that kinetic energy is 1/2 mv squared, so I'm going to substitute gm over r for the v squared, and I end up with 1/2 m gm over r. And reorganizing it, I basically have 1/2 gmm over r, and recognizing the gmm over r as potential energy or negative potential energy, I have kinetic energy now equal to minus 1/2 the potential energy. Okay, so again, remember that derivation where we stick centripetal mv squared over r equal to gmm over r squared, okay, gravitational force. Okay, taking a look at that third step where v squared is equal to gm over r, that is the equation that we use for orbital velocity when we take a square root of both sides. Okay, this equation is not on the formula sheet, so either memorize it or, better yet, know how to derive this in a very quick fashion. Okay, the other thing I want you to memorize is this graph. This is a graph of the kinetic energy, the total energy, and the potential energy. Okay. Kind of the way to remember this is my mnemonic that I use, which is keep it up. Okay, so K for kinetic energy, T for total energy, and P for potential. The kinetic and total energy are pretty much going to be reflections over the x-axis. If from an absolute value standpoint, they're exactly identical. The potential energy is going to be double the kinetic or double the total energy. So if you can remember that, this graph helps because I can think of different R's and what happens to my kinetic energy. Okay, so if I'm orbiting, my kinetic energy increases and my velocity increases as I get closer to the planet. My total energy decreases as I get closer to the planet. And my potential energy also decreases as I get closer to the planet. So this graph can help in several different ways, primarily for multiple choice problems and being able to answer them at a slightly quicker rate than having to derive stuff. So let's move on to the escape velocity definition. Okay, the definition for escape velocity is the minimum velocity needed to escape a planet's gravitational well. Or in other words, I'm the minimum amount of kinetic energy, 1/2 mv squared, to overcome the gravitational potential energy at the surface of the planet. So that's how we solve or calculate escape velocity. Okay, we take the gravitational potential energy at the surface of the planet, gmm over r. Okay, and we set kinetic energy equal to that, or 1/2 mv squared is equal to gmm over r. After some mild algebra, we find that escape velocity, v, is going to equal the square root of 2gm over r. This looks very similar to the orbital velocity, except there's a 2 now in the numerator. So this is partially why I don't recommend that you memorize them. They're so similar and it's very easy to get the two confused. It's easier to derive them and the algebra for that isn't hard. You just have to remember the process of doing so. Okay, so escape velocity. This brings up a couple of aspects that can be important, okay? So rocket launch sites are situated closer to the equator. And sometimes people ask why that is, okay? The reason being that the Earth is spinning and objects near the equator have a greater velocity than objects near the pole. Greater velocity implies that it has greater initial kinetic energy, and so you need to add less kinetic energy to launch an object into orbit. Okay, the Earth's rotation also means that your apparent weight at the equator is less than your apparent weight at the poles. Okay, so that's the end of this lecture. Thank you very much.